Let's take a look at the second and most prominent mural you'll see in the math hall at Walter Johnson High School. This mural, painted in spring 2023, displays the 13 Archimedean solids. They're named after the Greek mathematician Archimedes. The Archimedean solids are convex polyhedra that consist entirely of faces that are regular polygons, and the same types of faces meet in the same order at every vertex. The Platonic solids, remember, had the same requirements, but we were even more strict, requiring that all the faces be the same regular polygon. The Platonic solids are also called the regular solids. In the same way that our Archimedean solids are also called the semi-regular solids. There are 13 Archimedean solids, excluding the prisms and antiprisms, which we will say more about in a few minutes. Let's quickly name all 13, then we'll explain how we get them. In order, starting at the right end of the mural, we have the truncated tetrahedron, the truncated octahedron, the truncated icosahedron, the truncated dodecahedron, the truncated cube, and the snub dodecahedron. Then, continuing down the hall from right to left, we have the snub cube, the truncated cuboctahedron, the cuboctahedron, the rhombocuboctahedron, the truncated icosadodecahedron, the icosadodecahedron, and the rhombicosadodecahedron. Now let's jump into an explanation of each of these. All right, now that we've named them all, let's take a closer look at how these Archimedean solids are formed. Here, everyone grab your jar of Archimedean solids. Everybody's got a jar of Archimedean solids, I hope. And we're going to start with what we already know. Let me clean these up in a second. The Platonic solids. We're going to start with what you know about the Platonic solids. And so if you haven't already done so, stop and watch the video explaining the Platonic solids. The explanation for each of the Archimedean solids assumes that you're already familiar with the Platonic solids. So if you've done that, let's get into it. The first 5 Archimedean solids are pretty quick to explain. They are the truncation of each of the 5 Platonic solids. That is, we're cutting off the corners of each of the 5 Platonic solids. We've got over here, cutting off the corners of the tetrahedron. We've got the truncated tetrahedron, the truncated cube, where we cut off the corners. And these particular 3D printed models have the green parts being kind of the truncation, right? So where you cut off the corners, you get these green things, right? So we get the truncation of the tetrahedron, the truncated cube, the truncated octahedron, the truncated dodecahedron, and the truncated icosahedron. The truncated tetrahedron is the result of cutting off the corners of the tetrahedron. Now, as we do these truncations, we have to do them in such a way as to produce regular faces. If we do this carefully, think about what new faces you would have. The tetrahedron has 3 triangles coming together at each vertex, right here. So when you make a cut, what kind of shape are you going to get when you cut off this corner? That's right, you get a triangle. If you just take off a little corner at each vertex, leaving part of the original edges, then the original faces, which were triangles, now have twice as many sides. That's right, they're hexagons. These triangular faces become hexagons. You really do have to do this operation precisely, though. You have to cut at just the right angle, in this case parallel to the opposite side, right? You kind of slice it parallel to this desk so as to produce equilateral triangles. And you have to cut at just the right depth in order to produce here regular hexagons, where these white hexagons are. Those are places where there used to be triangles. If you cut even deeper so that the original edges completely disappear, can you imagine doing that? Like we cut at a kind of a shallow depth and just cut off the 4 tips, the corners. But if you cut even deeper, you can imagine if you had chosen to cut all the way deeper, then actually what you might get is not a hexagon here at all. You would cut so deeply that you would get these triangular faces. If you cut just a little, you get hexagons. But if you cut them really far, you get triangles. So think about that with me. If you were to do that and cut all the way to the center of each of these faces, each of these edges, you'll get new triangles here. You'll get 4 triangles for each of these faces, but you'll also have the 4 triangles that you got from the truncation. you're actually getting something cool, but it's not something new. It's actually going to be the octahedron again. This is not quite to scale. It would obviously be like a smaller octahedron, but the point is, I hope this will maybe be a little hard to visualize, but that's what you'll get. So that's worth mentioning, but let's move on to the next one. Now let's take a look at the cube. If we cut off the corners, again, just cut a little, what will we get? That's right, we'll get, at each of these corners, we'll get triangles. Now why is that? Well, it's because at each vertex we have 3 squares coming together, and so when we cut it off, we get a triangle. And the original faces will now have twice as many edges, so those squares will become octagons. Now, of course, we have to do this carefully in order to make sure that the triangles and the octagons that we get are regular ones. But if we do that, and we can, then we get this thing. It's called the truncated cube. Likewise, over here, we've got the octahedron, and if we do the truncation to it, every one of these vertices has 4 triangles coming together. And so when you cut off those, you get, that's right, you get squares. And just like the truncated cube, over here, each triangle, when you cut off its 3 corners, it produces 6 total edges, making each of the triangles, things that were triangles, are now hexagons. This is called the truncated octahedron. So we got the truncated cube and the truncated octahedron. If we go all the way, remember, this is what we did with the tetrahedron a minute ago. This is called the rectification. So in the last, I didn't mention it a second ago, but when we cut all the way as like far as possible, the tetrahedron, we created the octahedron, which is also kind of like the rectification of the tetrahedron. But here we've got a new thing that hasn't been discussed yet. This is called the rectified cube, or well, I'll give you the real name in a second here. This is, you can see if you keep cutting these corners all the way off, all the way down, so that now it was a square, now it's an octahedron, but if you kept cutting deeper so that we get all the way here, you get like another square. I've oriented it properly so that if you cut off deeply off of all 4 of these corners, you're going to get here this square. These are still going to be triangles, they're going to be even bigger now, but you're going to get this shape where these cuts meet each other in the middle. And this is called the rectification. That's what this process is, rectifying the cube. And so this is a brand new shape. I'm not going to give you its actual name yet. I want you to think about what happens with the octahedron. When you take its truncation, you get this, the truncated octahedron. But again, if you were to do it even more deeply, what would you get? Well, the answer is you would get this, wouldn't you? If you keep going, now I apologize, the colors here are not really compatible, but if you keep going, this square is going to get bigger and bigger, and these hexagons again are going to become, this edge here and here are going to vanish. You're going to get triangles right here. So this is not only the rectification of the cube, this is also the rectification of the octahedron. And so this is called the cube octahedron. Isn't that a great name for it? Because it's kind of this intermediary form between the other two. Now, if you watched the video explaining the Platonic solids, then you'll remember that the cube and octahedron have a special dual relationship that corresponds the vertices and faces of the cube and the octahedron. So perhaps it's not a huge surprise that when we rectify the cube and rectify the octahedron, we get the same thing, the cube octahedron. Well, we have 2 more Platonic solids to look at. Let's look at the icosahedron. The icosahedron has 5 triangles coming together at each vertex. So what happens when we cut off one of these corners? That's right, you get a pentagon, this green pentagon right here. And each face, which was originally a triangle, will become a hexagon. This is the truncated icosahedron. It's the famous soccer ball. It consists of 12 pentagons, where each of those vertices were originally on the icosahedron, and 20 hexagons, where the 20 triangles were. Now, let's look at the dodecahedron. If we cut off the corners, we'll get triangles, since there are 5 pentagons coming together at each corner. So you see these little triangles over here. And these were all pentagons before. So each pentagon becomes, well, it has twice as many edges. So now they're decagons. All of these white faces here are decagons. This is the truncated dodecahedron. It's got 20 triangles and 12 decagons. Now, if we do, again, that like full truncation, that is the rectification of either of these, maybe you're already guessing what's going to happen, and I've kind of set it up here, haven't I? This is the icosahedron, the perfect mix of the icosahedron and dodecahedron. So again, you can picture that happening by if you were to take this pentagon here and make it bigger and bigger, make that like truncation bigger and bigger until now it's a big one. And in here, each of these hexagons will become a triangle. Likewise, you could also think about it as being this one here, taking those triangles and cutting until they get to be big triangles. But now this is no longer a decagon. It was a pentagon. We cut off the corners. It was a decagon then. But then as we keep cutting off the corners, it becomes a pentagon again. The icosahedron in the middle. So I said we'd start with the 5 truncations of the 5 platonic solids. But along the way, we've also added these to the list too. So I think we're up to, well, these are all the Archimedean solids that we have just learned about here. Let me see if I can get them to show on the screen here. I should put these in the right places where they belong. There we go. Okay. And so there we have I think we're up to 7 of them. Someone might get excited about this idea of truncation. They might even ask, could we do it a second time? If we do this to the cube octahedron, one of those ones we just got a minute ago, we will get, well, let's take a look. We'll get squares here at these 4-fold vertices everywhere. All the vertices will become squares. The square will become an octagon, and the triangles will become hexagons. So sure enough, we can do this. There it is, the truncated cube octahedron. You can see that there they are. Each of those corners, when we cut them off, become these black squares. The green triangles are becoming hexagons, and the white squares have become octagons. Wonderful, except here's the issue. Here's the issue. This is a little bit of a lie. Let me show you. This is a cube octahedron. Thank you, Wikipedia. And if we actually do the truncation, look what happens. It might be a little hard to notice, but those blue things are not actually squares, technically. They're actually rectangles. So lies. But it is obviously, because it's sitting in front of you here, it is obviously possible to create this configuration. And so even though it technically isn't the truncation of the cube octahedron, we're still calling it the truncated cube octahedron. Sorry, everybody. It's just tradition. Now you might be thinking, could we do this to the icosahedron? And if you're thinking that, then you are right. Well, the same kinds of things happen, don't they? We've got these 4-fold vertices. Each one of those, where the 2 triangles and the pentagons meet, are going to become, every vertex is going to become a square. And then each of the pentagons, let's see, it's got 5 sides, so now it's going to have 10 sides. It's going to be a decagon, and then those green triangles are going to become hexagons. There we go. So there it is in all of its glory. This is the truncated icosahedron. Makes perfect sense, even though that at first when you heard these names, you're like thinking, how could anyone ever know them? But they make complete sense, right? This is the icosahedron. That made sense because it's like the intermediary form between the icosahedron and the dodecahedron. And this is us cutting off its corners, the truncation of that. So I think we're up to 9 total solids. Just dropped one on the floor, no big deal. Okay. We're doing some great progress on naming these things. All right, we're up to 9, and we have 4 more to go. So the last 4 solids we need to address arise from expanding the platonic solids outward. And what I want you to do is imagine taking this cube, let's start with the cube, and exploding outward all of its faces so they go kind of away from each other. When you do that, you're still going to have 6 squares. They're still going to be there. But they're going to be kind of farther away from each other. And then we're going to fill in all that extra space with other regular polygons. So each square, as they separate, each edge will become another square, right? Because filling in between an edge and an edge will give you a square as you move them parallel away from each other in a parallel fashion. Each of these 3-fold vertices will become a triangle because it'll create that triangular space between. You'll get something that looks like this, right? You can kind of imagine, you can still see the 6 faces of the square right here, can't you? And like I said, each of those edges is going to separate, and it's going to create a square as it moves. They kind of move away from each other. We really should have an animation up here, but you get what you get. Each of those corners we said was going to be a triangle. Now, let's also think about what would happen for the octahedron if you expanded it outward. And the thing you'd get, well, let's think about it. As we expand this outward, each of these fourfold vertices where these four triangles are coming together is going to become a square. Each of these sides, where these two triangles meet, as the edge separates, it's also going to create a square, and it might take you a second to visualize it. But the thing you get is, that's right, you get also this thing right here. And so this thing we've got here, it's the expansion of the cube. It's also the expansion of the octahedron. This is called the rhombe cube octahedron. A good name for it would also be like the expanded cube octahedron or something. But it's the expansion of the octahedron and the cube, the rhombe cube octahedron. Now, if you're thinking, can we do this with the dodecahedron too? And the answer is, of course, yes. What would happen when we expand on the dodecahedron? Well, each of these pentagons would still be a pentagon. You'd have 12 of them all moving away from each other. These edges, as they separate from each other, will become squares again, filled in parallel to each other, so they'll get a square. And each of these vertices, where three pentagons meet, will leave kind of a triangular gap to fill. And so we get this shape here, the expansion of the dodecahedron right here. You can see exactly all the things we just said. Now, if you're thinking, is that also the expansion of the icosahedron? You would be right. Yeah, in fact, you can even see the 20 black triangles that came from the 20 triangles from the icosahedron. So in both cases, we get this thing in the middle. So this is the rhombe cube octahedron. This is called the rhombe icosahedron. So with these two expansions, we're up to 11 Archimedean solids. We only have 2 more to go. And the last also arise from this kind of expansion idea. Let's do an expansion of the cube. But this time, as we expand the cube, I want you to think about something else. As we expand the cube, we could, instead of expanding it outward, here, we'll take a look at the cube here. Instead of expanding it outward and just like pulling them straight apart in all directions, what I'd like to have you think about doing is, as you pull them apart, I want you to give them, as you're pulling them apart, a little twist. And when you do that, things are dropping on the floor. One thing that's happening is you get this thing right here, which is the snub cube. Notice the thing that's happening here is, it's a little hard to see on the video, but you've got this twisting. These white squares on opposite faces are like 45 degrees apart. They're like squares that are not directly apart from each other, right? They're like twisted. One, you could think of like one twisting 22.5 degrees and the other twisting 22.5 degrees as they separate. And then you fill in with triangles. That's called the snub cube. Now, some people might also call it like the snub octahedron as well. You can kind of see that octahedral structure in there too. But the snub cube is what it is typically called there. Okay, and then of course you can, last one, we're doing it. The last Archimedean solid is the snub dodecahedron, and that happens by doing the same thing. Take the dodecahedron, and as you're expanding it, twist it as well, and you're going to get 12 pentagons still, but then you're going to fill it in all with triangles. Now, I will also say, the person who made these 3D printed solids for me included these. So you might have thought, well, they included some bonus ones just in case you lose them or something. No, not quite. Notice that we typically only say there are 13 Archimedean solids, but honestly, if you twist one way or the other, you actually get something that is not necessarily the same. These are actually technically not the same. At first glance, they might look the same, but they're kind of mirror images of each other through space. So, but we don't usually consider them as being separate ones. So we've got them all. Here are the 13 Archimedean solids. We're bringing them back to view. I'll remove one of those just so you can see them. There they all are. Aren't they pretty? Now, there's an important footnote we need to mention before we close out this video. It turns out that there are some other solids that meet the definition of Archimedean solids. That is, namely, the prisms. Well, not just any prisms, but those that are created by taking 2 regular polygons and connecting them with squares at right angles. There are an infinite number of these. The one we see here is the pentagonal prism. And wait, there's more. You can also form antiprisms of any size. This is the pentagonal antiprism. The way we get this is by rotating the pentagons by half an edge. In this case, 36 degrees will do the trick. And then you fill in with triangles pointing up and down. There's nothing special about the pentagonal antiprism. You can do this with any regular polygon. So this is also an infinite family. Do these meet the definition of the Archimedean solids? Yes, actually. The faces are all regular polygons, and every vertex has the same arrangement in the same order. We have a pentagon and two squares that meet at every vertex in the pentagonal prism. And in the pentagonal antiprism, we have a pentagon and three triangles that meet at each vertex. So after a very careful explanation of the 13 Archimedean solids, are we saying there are actually an infinite number of them? Well, yes, kind of. The semi-regular solids are really the 13 we've talked about, plus an infinite number of prisms and antiprisms. Let's review. The Archimedean solids are convex polyhedra that consist entirely of faces that are regular polygons, and every vertex has the same arrangement of faces in the same order. There are 13 Archimedean solids, excluding the prisms and antiprisms. Again, starting at the right end of the mural, we have the truncated tetrahedron, the truncated octahedron, the truncated icosahedron, the truncated dodecahedron, the truncated cube, and the snub dodecahedron. Then, continuing down the hall from right to left, we have the snub cube, the truncated cuboctahedron, the cuboctahedron, the rhombocuboctahedron, the truncated icosahedron, the icosahedron, and the rhomboicosahedron. Aren't these beautiful? I hope the next time you walk down this hall, you'll stop to appreciate these more deeply and start seeing them as friends. Maybe you'll even remember their names. If you think you can name them all, please come and see me. I'd love to quiz you. If any of you are interested in taking a deeper dive, trust me, the polyhedron rabbit hole is very deep. You might start your journey by looking into the 13 Catalan solids, that is, the duals of the Archimedean solids, and the 92 Johnson solids, in which we relax the vertex arrangement requirement. Thanks for listening and learning a bit more about the WJ math murals. Until next time, may the joy of math be with you.